3.5, division of whole numbers. This is our last section of chapter 3. Once we're done with this one, we will be at a point where we'll be taking in our next exam. This one's not quite as long as the other sections have been, a little bit shorter, kind of like the subtraction one was. So to start with, we're going to define what we mean by division. If we have whole numbers a and b, b is not 0, then we say that a divided by b is equal to c, if and only if c is the unique whole number such that b times c is equal to a. Just fill in the gaps for now and we'll talk about it in just a second. We call a the dividend, we call b the divisor, and we call c the quotient. Okay, so we're going to use numbers. So let's say that we have 12 divided by 3. So this is going to equal something. And what we usually do when we teach division is we try to think about it as the reverse of multiplication, right? So if a child is doing 12 divided by 3, you probably would ask them something like, what do you have to multiply 3 by in order to get 12? Right? So this question mark, if you will, is coming over here on the same side as the 3 to be multiplied by the 3 to get you back to 12. And that's what this is defined as, right? It's saying that the C is coming over to the same side with B, and the result is the value that you started with, A. Okay. It's changing it using fact families. It's changing it to its multiplication form. 3 times what is 12? Oh, it's 4. And then we've got the answer is 4, so we could fill these in. This number is the number 4, because this number is the number 4. So the number that we divide by is called the divisor. This one is the divisor. The number that is being divided is called the dividend. And the answer to a division problem is called the quotient. Okay, so we're going to do 3 models for division. They aren't so much that the division looks different in terms of the question, like our other models have been, but they're thinking about it in terms of how we solve it. Okay, so this is going to feel a little different than the other sections that have these models in it. All right, Junie has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So this is the same question that we're going to see over here for partition. Okay, they're the same question. But a repeated subtraction model is the idea of taking all the 24 rocks and having her 6 friends sort of in front of her, and her going, you get a rock, and 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 then we just start over and we go back through, right? So we go back around and around and around until we've repeatedly subtracted or removed all the 24 rocks from Junie. Okay? The way that we write that down, though, is that we're not going to write -1, -1, -1, like that would be a lot of work, is that we're going to subtract, you're still going to think it's a lot of work, by the way, you're going to subtract the number of rocks she hands out in one rotation of friends. There's 6 friends. So once every friend gets one, she has removed 6 rocks from her collection. And you're going to subtract it, and you're going to get that this is an 18. And then you're going to do the same thing again. Okay, they all get one more rock. So we subtract 6, you get a 12. They all get one more rock. You subtract 6 and you get a 6. You all get one more rock, and then there's either 0 at the end, or there's something that's too small that we can't continue to do so, right? Junie maybe has something left over, but they can't all split them up. That's a possibility. All right, so the question is, how many rocks did they each get? Well, what we do is we go back and we count how many times we went through the cycle of going through each of our friends. We did it 1 time, 2 times, 3 times, 4 times. So every subtraction of 6 was a giving of a rock to each friend. So each rock was given a friend. Each rock was given a friend. Yes, that's good. How about each friend was given a rock? Each friend was given a rock how many times? 4. So the answer is 4 rocks. Now, there is an extension to this when the numbers get bigger. So bear with me. We're not going to subtract 6 from the number 3,000 or something like that. That's not what we're going to do. There's an extension to that, okay? But for a small value, and this is the concept of the idea, is that I'm removing something repeatedly, okay? The next model is the set partition model. There are two set partition models. These are variations of one another. So the first one says the same problem that the original one for repeated subtraction said. Junie has 24 rocks. She wants to give them to each of her friends. How many rocks will each friend get? So this idea is to take 24 rocks, and so we're going to draw 24 rocks. I'm just going to put them in an array just because it's easy to kind of put them all together and see that I've got them all. So I've got 24 rocks here. And she partitions them into 6 groups. She needs 6 groupings of them when she's done. So she collects them and she makes one group, and she collects and she makes another group. And so we're trying to create 6 groups of rocks. Now, the way I drew them was actually kind of nice, and it wasn't really intentional because I did them in an array, which is a 4x6 array. If I had done them, in a 3 by something, it might not have worked out so nicely to see it. But because I have 6 rows, you can see easily that I have 6 groupings. There's 1, 2, or you can see what the grouping sizes are, I guess. 3, 4, 5, and 6, right? There are 6 groupings. There are 6 groups of specifically 4 rocks, and 4 would be my number of rocks each friend gets then. Okay, so this is one version of a set partition. There's another version of a set partition, and the language does change a little bit. Junie has 24 rocks. That part didn't change. She bags them together in a group of 6. So now it doesn't say she has 6 friends. She's making groups of size 6. Can you picture that? So each group is going to have 6 in them now. If she gives one bag to each friend, how many friends will get a group of 6 rocks? Now that's a different question than we had before. Over here, we had a predetermined number of groupings or number of friends, right? Here we have a predetermined size of each group. Okay, so our classroom in here is not a great example because there's only 6 of you. But when you have a large classroom, so let's say you had 20 children in your classroom, that would be pretty realistic for most elementary school classrooms, 20 or so. You get to determine one of 2 things when you put kids in groups. You either get to determine the number of kids per group. Maybe you only want 2 kids per group or 3 kids per group, right, for whatever reason. Maybe it's an activity that they all each have a role to play, right? So you get to determine the number of kids per group, or you get to determine the number of groups in your classroom. Now, obviously, those things affect one another. That's not the question. But sometimes you really need the groups to be a certain size, and sometimes you really need to not spread yourself around between 12 groups in the classroom, right? If you could make the groups just a little bit bigger, you'd only have 8 groups to go to, or something like that. So you'd have fewer people to meet with as a group setting. Okay, so there's 2 ways to do groupings. One is to determine the size of the group. That's what we're about to do here. The other is to determine the number of groups. So if we're determining the size of the group, we can have still our 24 rocks. Okay, so here's our 24 rocks. But instead of having 24 rocks and splitting them among the 6 friends, I need to make groups that have 6 rocks in them. So here's 6 rocks, and here's 6 rocks, and here's 6 rocks, and here's 6 rocks. And once I put these 6 rocks apiece in each of the bags, I end up with 4 bags of rocks. So there are 4 bags of 6 rocks, meaning that I can give them to 4 friends. Does that make sense? Now, the tricky thing is that some of these, like repeated subtraction up here, and the set partition model, the first version, they're the same question, they're just a different way of thinking about it, right? Set partition model from the first one to the second one are actually set up differently. However, your book does not specify between the two. It doesn't give any indication of them being somewhat different. The reason I point it out is because when you get to proportional and statistical reasoning, or for those of you who've already been here, it's this second one that works better for fractions. I can't say, I have 24 rocks and I wanted to give it to one half of a friend. What is one half of a friend? Like, that doesn't make any sense, right? And rocks aren't a great example because I can't break them apart. Let's do cookies. I have 24 cookies, right? I have 24 cookies and I want to give half of a cookie to each friend. How many friends can get half of a cookie? I can do that, right? I can give out half of a cookie. I can't have half of a friend. So this version, the second one here, is actually the one that blends nicer into working this idea of division with fractions. Okay, we have one more model. The last model is the missing factor model. And again, it's not any different than the first one that we did, the first two. It's just a different setup. So it says they have 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So what we're saying here then is that we're doing 24, and we're giving them to a certain number of friends, and each of the friends is going to get, oh, I didn't use the second one, I'm sorry. She wants to give, no, I didn't. I did it right. 6 of her friends. Yeah, equals 6. That's what I want. She wants to give the friends, give the rocks to the friends. She has 6 friends. How many rocks does each friend get? And so we set it up as being a division problem with a missing factor, much like we saw at the beginning, or you can set it up like this if you wish to. 6 equals, looks probably a little bit more like what you did at the beginning. It's not what my notes say, but I like this a little bit better for what we've done. So 24 divided by 6, and you change it into a multiplication problem, and you say, but this is 6 times something is equal to 24. Well, what is 6 times something? What is that something? It's a 4, right? So 24 divided by 6 would have been 4, and each of my friends would then get 4 rocks. All right, so we're going to push pause right there. When we come back next time, we're going to, depending on our timing of how long questions take, we will either jump into you guys doing some examples, like where you created them, like we've done before, or we might skip that portion of it to finish up 3.5, okay?